Pratt & Whitney's F-135 engine is the undisputed heartbeat of modern air superiority. It generates 43,000 pounds of thrust while maintaining a near-zero radar signature, allowing the F-35 to operate deep within contested airspace. This single-engine platform powers 3 distinct military variants, including the Marine Corps version capable of a full vertical hover and short-field landings. The scale of the program is immense. These engines are currently deployed across 20 allied nations and have accumulated over 1 million flight hours in both training and active combat. The F-135 is the foundational pillar of global allied defense and a massive economic engine, supporting more than 67,000 American jobs. But in May of 2024, a Government Accountability Office audit revealed a startling breakdown in the program's actual delivery performance. According to the GAO, Lockheed Martin delivered 91% of its aircraft late in 2023. Even worse, Pratt & Whitney delivered 100% of its engines behind schedule. This catastrophic bottleneck has nothing to do with a lack of funding or engineering talent. The money is there, and the factories are running. The enemy crippling the world's most advanced fighter jet is just a basic physical reality: unmanaged internal heat. It seems simple, but this thermodynamic limitation has the power to halt a $2 trillion military supply chain. To understand why, we have to look at a design choice made nearly 20 years ago. In 2005, engineers celebrated a breakthrough in how the F-35 would handle its internal power and temperature controls. They developed the Integrated Power Package, or IPP. To save weight, they merged auxiliary power, emergency systems, and environmental controls into one unit. The trade-off: the IPP relies entirely on the main engine to generate the air pressure needed to cool the jet's complex electronics. This integration created a single point of vulnerability. The engine was now permanently responsible for both propelling the aircraft and keeping its computer systems from melting. Today, the F-35 is undergoing a $1.8 billion modernization known as Technology Refresh 3, or TR3. TR3 introduces new hardware, including a core processor with 16 times more power and a memory system 20 times more capable. But these digital upgrades have a physical cost. Running processors at these speeds generates immense excess heat the jet must dissipate. This is where the 2005 design met a hard limit. As early as 2008, engineers realized the original F-135 engine couldn't provide enough cooling air for the high-demand electronics of the future. However, redesigning the engine at that stage would have caused massive schedule delays and cost overruns. To keep the program moving, leadership decided to stick with the original cooling capacity. Today's delivery backlog is the direct consequence of that decision. The engine is being forced to work beyond its physical limits just to keep the jet's new brain from overheating. This has created a state of paralysis. The broader Block 4 modernization cannot move forward until the aircraft receives a massive, yet-to-be-built thermal management upgrade. Despite the urgency, the Department of Defense has not yet fully defined the new cooling requirements or awarded a contract to fix the problem. This technical indecision leaves the multi-billion-dollar future of the Block 4 program at high risk. It is a stark irony of modern warfare. Billions of dollars in advanced software capabilities are effectively grounded because the physical airframe cannot regulate its own temperature. The aerospace industry is now applying these hard lessons to the next generation. Pratt & Whitney is currently developing the XA-103 engine for future fighters. It uses an adaptive cycle design, which allows the engine to dynamically shift its physical geometry between maximum thrust and fuel-efficient cruising modes based on the mission. Crucially, the entire digital design of this engine is built around the thermal and power demands that cripple the F-35's modernization. Winning in the 21st century is no longer about outflying a missile. It is about designing hardware resilient enough to survive the fiery, relentless pace of software evolution.